Welcome, everyone. I'm excited to have you here today. We're about to dive into an overview of compressor types, design, application, and commissioning. This presentation will also cover key topics like selection, sizing, standards, installation, and maintenance. Over the next few slides, we'll explore these areas in detail to give you a comprehensive understanding. Let's get started. Let's talk about compressor classification. Compressors are devices that increase gas pressure by reducing its volume. They play a crucial role in many industrial processes. The main categories of compressors are twofold. First, we have the positive displacement type. These compressors work by trapping a certain volume of gas and then compressing it. Examples include reciprocating, rotary, scroll, and screw compressors. The second category is dynamic or velocity compressors. These impart energy to the gas through high-speed impellers, and typical examples are centrifugal and axial compressors. Understanding these categories helps us choose the right compressor for specific applications. Now, regarding the power requirement for compression, there's a fundamental formula. Power equals the mass flow rate times the gas constant times temperature, divided by efficiency, all multiplied by the natural logarithm of the pressure ratio. For instance, if we consider air flowing at 100 kilograms per hour, with an inlet pressure of 1 bar and an outlet pressure of 8 bar, and an efficiency of 75%, the power needed would be approximately 7 kilowatts. This formula and example highlight how factors like flow rate, pressure change, and efficiency directly impact the energy consumption of compressors. Understanding these points helps us optimize compressor selection and operation within our overall system. Let's take a closer look at the reciprocating compressor. This type of compressor operates using a piston and cylinder mechanism, which can be configured as either single-acting or double-acting, depending on the design. The key idea here is that the piston moves back and forth within the cylinder to compress the gas. These compressors are commonly used in applications like refrigeration, small HVAC systems, and even gas bottling processes. One of their main advantages is their ability to generate high pressure, even at low flow rates, making them quite reliable for these specific uses. When it comes to standards, reciprocating compressors typically adhere to ISO 13631 or API 618. Which ensure safety, efficiency, and consistency across different models and manufacturers. Now, if you're sizing a reciprocating compressor for a project, you can use this formula. Q equals pi times the diameter squared, times the length, times the rotational speed, times efficiency, times a constant K, all divided by 4. This helps us determine the flow rate, which is crucial for matching the compressor to the application's needs. Overall, understanding the design and application of reciprocating compressors is essential as they play a vital role in many industrial and commercial systems. Let's take a closer look at the rotary and scroll compressors. These are designed with an eccentric rotor or an orbiting scroll that compresses gas continuously, which helps improve efficiency and reliability. You'll often find these compressors in split and packaged air conditioning units, VRF systems, and chillers that are under 200 tons of refrigeration capacity. One of the main advantages is their compact size, making them ideal for space-constrained applications. They also operate with low noise levels and have fewer moving parts, which generally means less maintenance and longer lifespan. In terms of standards, these compressors conform to ISO 1217 and ARI 540, ensuring quality and performance consistency. For example, a 10-ton VRF unit typically uses a scroll compressor with a power rating of around 7.5 kilowatts. Overall, these features make rotary and scroll compressors a smart choice for efficient, reliable, and quiet cooling solutions in various HVAC systems. Let's take a closer look at the screw compressor. Its design features 2 intermeshing helical rotors that work together to trap and compress air efficiently. This design is quite popular in various industrial applications. For example, you'll find screw compressors used in industrial chillers, central air conditioning systems, and process plants where reliable, continuous compression is essential. One of the key advantages of screw compressors is that they provide a very smooth airflow, which helps reduce pulsations and noise. They also offer high capacity, meaning they can handle large volumes of air, and they tend to operate with low vibration levels, contributing to longer equipment life and quieter operation. When it comes to standards, screw compressors are typically designed and tested according to ISO 10441 and API 619, ensuring they meet specific quality and performance benchmarks. And if you're interested in the performance calculations, there's a specific formula used to determine power consumption, which involves parameters like flow rate, pressure ratio, efficiency, and the specific power formula. Understanding this helps in optimizing the compressor's operation for different applications. Overall, the screw compressor's design and advantages make it a vital component in many industrial and commercial systems, aligning perfectly with our theme of efficient and reliable compression technology. Let's take a closer look at the centrifugal compressor. This type is classified as a dynamic compressor, which means it uses the impeller to accelerate the air outward. The impeller essentially spins at high speed to increase the air's velocity. Then, the diffuser plays a crucial role by converting that high velocity into increased pressure, making the compressed air ready for use. In terms of applications, centrifugal compressors are typically used in large chillers, specifically those over 250 TR, gas turbines, and refinery air systems. They're well suited for these heavy-duty tasks because of their ability to handle high volumes efficiently. One of the biggest advantages of centrifugal compressors is their ability to deliver a continuous flow of compressed air without interruption. Plus, they are oil-free, which is essential in many industries to prevent contamination. They also tend to be very efficient, especially at high loads, making them a reliable choice for demanding applications. Regarding standards, these compressors usually conform to recognized specifications like API 617 and ISO 5389, ensuring quality and consistency across different designs and manufacturers. To give you a concrete example, consider a 500 TR chiller. Its impeller would typically spin at around 25,000 RPM. This high rotational speed is what allows it to achieve the necessary compression in such large systems. Overall, the centrifugal compressor's design and capabilities make it a key component in many industrial processes, especially where high flow and efficiency are critical. Let's talk about the axial compressor. This type of compressor is designed with multiple rotating and stationary blades that work together to compress gas along the axis of flow. It's a very efficient way to increase pressure, especially in applications where high flow rates are needed. You'll typically find axial compressors in jet engines, large gas turbines, and high-flow HVAC systems. These applications benefit from their ability to handle large volumes of air or gas quickly and efficiently. Regarding standards, axial compressors are often designed and tested according to ISO 10439 and ASME PTC 10. These standards help ensure safety, reliability, and consistent performance across different designs. Now on to the formula. Delta equals rho times V squared times the difference between the tangents of the blade angles, specifically tan beta 2 minus tan. This formula essentially relates the pressure increase to the flow velocity and the blade angles, which influence how effectively the compressor can increase pressure. Understanding this interaction is key to optimizing compressor performance, especially when designing for specific applications or efficiency targets. It ties neatly into the overall theme of how we engineer and refine turbomachinery for maximum efficiency and reliability. Let's take a closer look at the selection and sizing guidelines. When choosing the right equipment, it's crucial to consider several key factors. First, flow rate, which can be measured in CFM or cubic meters per hour, tells us how much air needs to move through the system. Next, we look at the pressure ratio, which is the outlet pressure divided by the inlet pressure, giving us an idea of the pressure differential the equipment must handle. Power demand is also vital. It's typically expressed in kilowatts or refrigeration tons and helps us understand the energy requirements for the application. Speaking of applications, these guidelines are applicable across various fields like HVAC, industrial air systems, and refrigeration, each with different demands and operational considerations. To give you a practical sense, let's look at a sample reference table. For reciprocating compressors, we're talking about flow ranges from 10 to 100 CFM, with high-pressure ratios and a typical efficiency of around 75%. These units tend to require high maintenance. Screw compressors handle larger flow ranges, from 100 to 3,000 CFM, with medium pressure ratios and about 85% efficiency, requiring medium maintenance. Finally, centrifugal compressors are suited for even larger flow rates, over 3,000 CFM, with lower pressure ratios and the highest efficiency at around 90%, and they generally demand less maintenance. Understanding these guidelines helps us make informed choices tailored to each specific application, ensuring we select equipment that's efficient, reliable, and suited to the operational demands at hand. Now, let's walk through the final step, installation and commissioning. First, we start with the foundation and vibration isolation. It's crucial to ensure the base is solid and properly isolated to prevent any operational vibrations from affecting performance or causing damage. Next, we move on to leveling and bolt alignment, which are vital for smooth operation and to avoid undue stress on the equipment. Then, we connect the suction and discharge piping carefully, making sure all connections are secure to prevent leaks and maintain system integrity. After that, we handle the electrical and control wiring, ensuring all connections are correctly made according to standards to guarantee safety and reliable control. Once the hardware is in place, we fill the system with oil and perform leak tests to confirm there are no leaks and everything is sealed properly. Following that, we conduct a rotation check, perform a Megger test, and run the equipment without load to verify everything is functioning correctly before applying any operational load. Finally, we carry out a load test, during which we record key parameters like pressure, temperature, and vibration. This comprehensive testing ensures the system operates efficiently and reliably. Throughout this process, we adhere to standards such as ASME B3015, ASHRAE 15, and API startup procedures, which provide a solid framework for safe and effective commissioning. This step is essential to ensure the equipment is ready for long-term, trouble-free operation.